Oh my goodness. So the last part of this one is to find, let's see if I can make some room here, is to find how much off course is this wind blowing the airplane. So our original course was 100 degrees. We were going 290 miles an hour. And we figured out that the plane is actually moving 293.5 miles per hour. And it's going at a different angle, and that's what angle we have to find. Well, we know that the angle is 45 degrees, so we're going to find the angle. Tangent is going to be 45 over 290. And if I do the inverse tangent of both sides, I get that my angle is equal to 8.8 degrees of drift. So it's drifting 8.8 degrees. So if it was originally going at 100 degrees, then its drift was 8.8 degrees. So it's actually flying at 91.2 degrees. And that would be the course. That's the plane is actually going at that course. So it does make a difference. That 8.8 degrees would put you off by quite a ways wherever you're flying to. All right, so then let's get to 9.4. Another example of an application of vectors is when you're describing a position or position as indicated by a magnitude, which is a distance, and a direction, which is relative to the starting point. So a vector describing a position is called a position vector. Each vector can be broken down into the component parts, and we did that with the previous one where we had the x component and y component. And we put them in a vector form. You see the pointy brackets. So the A is the x movement and the B is the y movement. So if I suppose that I am at a -1, 4, if I'm starting there, and I'm going to move using a vector of 3, -7. So I'm going to be moving 3 and then -7. So I'm going to go 1, 2, 3, 4, 5, 6, 7. So I'm going to end up finding using that vector. And where do I end up at? Well, I end up at, if I start at -1 and I move 3 to the right, I'm going to end up at the point, it's a point now, 2, and if I'm starting at 4 and moving down 7, I end up at -3. So I use the vector to move from one point to another point. A bumblebee begins on a flower at the coordinates 3, -2. And meanders for a while and ends up on a flower at -5, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. Give or take a half mile, about right there. Draw a position vector that describes the bumblebee's change in position and determine its magnitude and component vector. So we're starting there, we're ending there. So if I count, I know I'm going, my x position is changing by a value of 8 in the negative direction. My y value in a positive direction, up is a positive direction. So my vector in component form would be -8, 6. And if I want to find my magnitude of my bee's movements, we would use the square root of, we could use the points that are given. So I'm going to use 3 minus -5 squared plus -2 minus 4 squared. And shocker, shocker, we get that 8 and 6 numbers. And we know that that's going to turn out to be 10 because it's the 3, 4, 5 times 2. And what else? Magnitude is 10. Component vector we found was -8, 6. I think we found all the stuff that we needed to. The same bumblebee is still meandering from flower to flower. Now suppose that it is at 4, negative 3. Going to need a little more room here. 1, 2, 3, 4, negative 3 puts me there. From here, the bee first travels according to the vector negative 1. So 1 to the left and 2 down. So there's one vector. And then by a second vector, which is negative 3, 1, 2, 3, up 3, 1, 2, 3. And so the second vector moves it over there. First, determine the final position of the bee. So the bee ends up, it appears if the bee is over here at 0, negative 2, where it ends up. And verify your answer by drawing the path of the bee travels. Well, I guess I found that. Now, could we find that vector that goes from there to there? Absolutely. The resultant vector we could find. We know that that resultant vector ends up being 4 to the left and 1 up, the way it looks. 4 to the left and 1 up would be the resultant vector of that. Okay. And if we look at our vectors that we started with, can you see how a negative 4, 1 could come about? Vector addition. If we have two vectors in component form, we can add them together. The sum would be the sum, the A plus the C, and the B plus the D. And we just did that in the previous example. So to add vectors algebraically, we add their corresponding components. Scalar multiplication is when you multiply both. So if I had a vector just moving a distance 1 in that direction, a scalar multiplication would just make that twice as long, if C was 2 in this case. Scalar or vector subtraction, it goes how you think it would go. You add the opposite, or you can subtract. So if you subtract, you add the opposite over here. Same dealio. We perform a subtraction by adding the opposite of the vector we are subtracting to end up getting the other diagonal of the parallelogram formed in the addition. So instead of adding the V, we would subtract it. And if we put these together, you would get the same parallelogram. So let's say A, my first vector is 3, negative 1, and B is 0, negative 2. And I want to show that what 2A minus B is. So 2 is one of those scalars. So if I take 2 times A minus B, which would be 6, negative 2, plus a negative would make this positive 2. And then you add the scalars together and I get 6, 0. Okay? A unit vector is of length or magnitude 1. Two commonly used vectors is the I vector, which is a movement in the x direction of 1 unit. The J is the movement in y. And so you'll see vectors, instead of in component form with the fancy brackets, you'll see it in the IJ form, in which case if I had a vector of 3, 5, you would see 3I plus 5J. And these are just two different forms of writing the same thing. And let's take a look at a couple examples here. If I want to find out what this is, this is a scalar, so we're going to call this 15, 9 minus, or we can go plus 4, -6. And that gives me a vector of 19, and 9 minus 3 gives me, or 9 minus 6 gives me 3. And then if they want that vector in ij form, they would say 19i plus 3j. So 19i plus 3j would be another way of writing that. Express the vector in this format. Again, we know that I and j are just 1. So I'm going to say this is j. And if I want to find the magnitude here, which this is asking, I have to do the distance formula because I is unit 1. So I'm going to say 1 squared plus 1 squared gives me square root of 2. So that would be the square root of 2. And so when I simplify this, I get 1 over the square root of 2i minus 1 over the square root of 2j, which is the same as root 2 over 2i minus root 2 over 2j. So that's just going the diagonal. Okay? And find a unit vector having the same direction as that. Well, to find a unit vector, we need to take our, I'm going to write it in component form, 8, -9. And then I'm going to take that and divide that by its magnitude. So to find its magnitude, I'm going to take 8 squared plus -9 squared square root. I get 64 plus 81 gives me the square root of 145. So if I take each of those divided by its magnitude, I'm going to get and just for the fun of it, I'll rationalize, and I get the 8 square root of 145 over 145, comma, -9 root of 145 over 145. And so we know that those are 1 unit long, and if you wanted to, you could take that and put it in Pythagorean theorem and figure out how long it is. With the given angle measured counterclockwise from the positive x-axis, determine the unit vector u in the component form that passes through the terminal side of the angle. So we're talking about, we want to find something on the unit circle that meets right there. Well, if we look at that, it just so happens the point on the unit circle, because the unit circle is 1 unit long, we know that the value here is -1/2 -3 over 2. And so if we plug that into the Pythagorean theorem, we would get 1 because it's on the unit circle. So let's save this page for the next video.